can steal half of your EV range and run a battery faster than you think. Today we are breaking down what really happens to the electric car batteries when the thermometer drops. You'll see why some packs die on cold mornings, why charging slows to a crawl, and what engineers actually do to fight freezing temperatures. Stick with me, and by the end, you'll know which problems are solvable, which ones are ugly, and what a real winterproof EV needs. Imagine your battery as a subway full of tiny ions trying to run to the next station. At room temperature, those ions move fast and easy. Drop the temperature, and the subway tracks get icy. The ions slow down, the internal resistance goes up, and the battery can't deliver the same power that shows up as lower range. Weaker acceleration and longer charging times are also the consequence. On a chemical level, cold weather changes three big things. The electrolyte gets thicker and more sluggish. The solid layer that forms on the anode, called the SEI, becomes less forgiving, and the metal lithium itself wants to plate on the anode instead of folding neatly back into the structure during fast charging. Lithium plating is the real villain because it steals capacity and can start irreversible damage. Different battery chemistries cope differently. Cells with nickel-rich cathodes used in some high-energy packs perform well at room temperature, but suffer in power when cold. Lithium iron phosphate cells behave differently. Some LFP packs show less dramatic voltage sag in cold discharge, but still suffer during fast charge because of plating risk. The specific electrode coating, electrolyte formula, and cell design make a huge difference. That is why two cars rated the same in summer can feel like different cars in winter. From an engineering point of view, the symptoms are familiar. At minus 10 degrees Celsius, an average EV can lose 20 to 40% of usable range depending on driving style and cabin heating. At minus 20 degrees, that loss grows and charging times stretch, sometimes doubling. The charge curve itself changes. Instead of being able to accept high power at low state of charge, the pack limits current early. That protection keeps lithium from plating but leaves driver waiting and frustrated. Beyond the immediate loss of range and charge speed, repeated exposure to cold and charge cycles can accelerate degradation. Cold cycling stresses the SCI layer and can increase internal resistance over hundreds of cycles. In practice, that means a battery that once held 100% of its capacity could drop faster over years if it spends a lot of time charging at low temperature. So here's the big problem engineers face. How do you let drivers have fast charging and full performance in freezing weather without cooking the battery in the process? Help the battery warm up fast enough to accept power, but don't waste energy or create new failure modes. Make the system robust in extremes while keeping costs, weight, and the complexity acceptable for mass market car. Thermal sensors and cell monitors are less reliable at low temperatures. Grease and adhesives can shrink or stiffen. Connectors behave differently. You can design an incredible thermal system in theory, but if the sensors lie, the control software will make the wrong calls and either throttle the pack overly conservative or damage cells. Engineers attack these problems on multiple fronts at the same time. First is preheating and thermal management. Modern EVs use battery heaters, heat pumps, and clever insulation. Preconditioning the pack as soon as navigation says you're going to the charge is common. The car warms the battery to a safe window before fast charging starts. That costs energy and time but protects the cells. Second is smarter charging algorithms. The battery management system watches voltage, temperature, and internal resistance to decide how much current to allow. It slows the current at the first sign of plating risk and angles the charge curve to keep the electrochemistry stable. Better algorithms learn from repeated conditions and adjust more aggressively when they see patterns. This is chemistry and cell design. Some cells are made with additives in electrolyte that keep lithium from plating so easily in the cold. Others use thicker copper or different anode treatments to distribute current better and avoid local hotspots. Mechanical design matters too. Cells that are tightly packed will conduct heat differently than those with more spacing. Thermal pads cooling plates, and where you put heaters make a big difference. Fourth is software and prediction. Navigation integrated thermal management is becoming normal. The car predicts a fast charging stop and starts warming the battery en route. That simple trick can turn a 10-minute warm-up into a 10-second tap and go when you arrive. Fifth is testing and qualification. Automotive engineers run batteries through climate chambers, driving cycles, and cold soak tests that last for hundreds or thousands of hours. They force charge-discharge loops at minus temperatures to identify failure modes. These tests are expensive and take time, but they are how you go from a lab idea to a production-ready pack. Sixth is system-level trade-offs. You can add more heaters and insulation and solve most cold problems. But that adds cost and reduces range because heaters use power. You can add active preheating that uses shore power in the garage to warm the pack before you leave. But not every driver will plug in overnight. So manufacturers balance user experience against cost, complexity, and energy efficiency. An engineering story helps bring this to life. Picture an OEM designing a luxury SUV for cold climates. Their test drives drove back-to-back winter loops. The early prototypes could barely manage repeated fast charges in a single day. Engineers tried three things in parallel: beefier heaters, a revised electrolyte formula, and a smarter BMS. The heaters fixed immediate charging behavior, but cut range during city use. The electrolyte tweak reduced plating risk but required new safety validations. The BMS allowed fast charging by dynamically optimizing current across cell strings. In the end, they shipped a package that used a blend of all three approaches. It worked under the test and passed regulatory checks, but the extra costs show up in the price. Here's the key truth: there is no single silver bullet fix. Extreme cold doesn't just make cars slower. It changes the rules of battery chemistry. Successful solutions come from layering multiple defenses. Warm the battery when you can, manage charge currents smartly, pick chemistries and cell designs that tolerate cold, and test relentlessly. When teams get all of these moving together, cars can charge almost like normal even in tough winter conditions. When one link breaks, the whole system shows its weakness. Imagine a commuter who needs a quick top-up at highway charger on a crisp winter morning. With good preconditioning and thermal planning, the car accepts the charge with only a small penalty. Without it, the charger doctor says, slow down, and the car goes into a protective crawl, leaving the driver waiting at the charger on the wrist. The contrast is the real pain point for the EV adoption in cold regions. To sum up, extreme cold heats EV batteries on three fronts. It slows the chemistry, it increases resistance and heat generation when you demand power, and it raises the risk of damaging side effects like lithium plating. Engineers respond with thermal system, chemistry tweaks, smarter BMS logic, and predictive software. The trade-offs are real. You can get excellent cold performance, but you will pay in cost, energy use, or complexity. The winners strike a careful balance and design for the actual conditions drivers face, not the laboratory ideals. If you want a deep dive into battery charging algorithms or breakdown of specific protocols related to battery management system, you can click on the BMS course in the description. Thank you.